projector to look at because normally that's how this works, how classes work. So there's a list of things. Still haven't wrote the test. So what's everybody curious about? Yeah. No.
Okay, can you look at the last year's how they did on the panel, or you write this one?
Yeah, I can do that.
Okay,
Yeah.
thank you.
So you don't end up doing like with the midterm and making it harder.
Right. Although since everything else has been harder, you should probably continue this theme straight. I'll take a look and see how everyone did. A lot of the time when I take off points, so it's kind of for a funny reason. There's this sign on the way home. I take my bike on this path up. So there's these Mayfair Lane and things. It parallels Bryden Canyon. Anyway, there's a sign at the front of it, and it says, "No motorcycle riding without consent of owner." So whenever I have one of my kids there, I'm like, so you're not allowed to ride stolen motorcycles on this path. You got to get the owner's consent. And the direct object of the sentence is the motorcycles. In a more philosophical sense, you could say that the sentence is about the riding of motorcycles. But either way, it doesn't even say path. I mean, there's nothing about the owner of the path on the sign. So obviously, owner refers to motorcycle. And
Grammatically, yeah.
yeah. So that's what the sign says. It's not what the placer of the sign thinks it means, but it's definitely what it says. This is why people dislike lawyers. They say something in a contract, and they have some idea in their head about what they think it might mean, but then they go to court, and the lawyer who's on the other side looks at it and reads it, and is like, well, this is what it says, and so this is what it means. And they're like, well, that's not what it means. So that's what it says. It's got your signature under it. Anyway, that's why people hate lawyers. I mean, there's other reasons too, but I think that's one of the biggest ones.
You're not wrong.
Anyway, so this manifests a lot of times on the questions. So here's an example, and I'm only talking to somebody else's. So you have some kind of thing like this. Okay, and so say something like char, message equals, and then we'll get some sort of, let's do this. Say that, message. Okay, so it's actually a list of strings. And we say something like printf, and we say it's some sign s, and char, message. Okay. That'll probably compile, and my guess is it actually does print out a message, but that's not quite what it says to do. It says make an array of strings, not an actual string.
So would that be an array with just one string in it so far?
Yeah, it's an array of one item. And so the cast there, the char star, like if we took it out, there'd be a question. What warning is the compiler, could even be an error. What is the compiler going to say is wrong with this line right here? I'd probably run it and be able to tell you if it's actually a warning or an error on the question. But
you're saying you need to print a string that the type you're printing is different.
yeah, it is. Yeah, you're giving it a pointer to a string, not just a pointer to a string. So anybody looking at that would say, well, that means to print out a message. So anyway, I think I'd probably take more questions off on things where people look at something and assume it means something when that's actually not actually what it means. And a compiler is like the most hated lawyer of all. It just comes in and does exactly what you said. Oh yeah, but what should I review? See, this is what I was concerned would happen. I'd show up for the review session and ask, what do you want? And everybody's like, we're experts on all that stuff. Yeah.
So for memory management, what exact points do you want to hit on there?
So I'd probably go for so we didn't go through a lot into the details of how the memory manager works, so probably not that so much. Perhaps Project 4 style memory management would make more sense than anything else.
Okay.
For example, you could say, here you go. I'll change this here a little bit, and I'll say, for I equals 0, I less than 100, I plus plus. This will be one kind of about how the memory manager works. Okay, okay. Star waste equals malloc 100 bytes. Okay, so the question here: how much physical memory is going to be wasted by this program? What's that? Oh, yeah, probably. I never did this.
Oh, good lord.
Control plus?
Okay, well, no, it's not in the terminal here. We have to open up the profile here and right there. Is that better? Okay, cool. Okay, yeah, something that takes a long time there. How much memory is that? Like physical memory?
Well, it's gonna allocate,
Well,
Wouldn't it be about 100 for each iteration?
because you're not freeing it, so isn't that allocating a total of 10,000?
so, yeah, kind of. The actual number is 0. The reason is, yes, you're allocating 10,000 bytes here, like you said. But the operating system won't actually allocate any physical memory until it's used.
Oh, that's right.
Right.
You're just allocating it, but so that it's there to be potentially used.
Right. You've used up part of the virtual memory space for your program, but the operating system will not have bothered to back out with physical memory since you didn't actually use it.
Good question, because everybody's sitting here doing math, thinking, okay, well, this is gonna, when really it's nothing.
Right. Maybe if you get multiple choice question, you have answers: 0, 100, 1,000, 10,000. What do you suggest? 800. 800. And then let's just see if anybody picks 0.
You just told us.
So let's say if we did allocate something that's over the amount of 10,000 bytes, then we have wasted memory. Yeah.
Well, here's where we have wasted memory. Suppose instead of this, we had, oh, here, we'll just do this. Okay, we'll just go ahead and fill it. J equals 0, J is less than 100, J plus plus. Waste at position J equals J.
Wasted position I.
Oh, that would be above. That would not do it. That would there you go. So now that we've actually stored something there, the operating system is going to have to back that with physical memory, since we're actually storing something in it. And so now we'll waste 10,000 bytes.
Before it was 0.
Yeah,
Virtual memory only.
right. Well, it was 0 bytes of physical memory before, since we hadn't used it. Yeah, so now like there will return it always returns a memory area as long as it can. But if we did something like, say we said malloc and 1024 times 2 is a megabyte, that's a gigabyte, that's a terabyte. Okay, at that point, if we say something like int star r space equals malloc, that whole thing there, we would actually cause an error if we said something like r space at position 0 equals 100. The reason that would give us an error right there is if we ask malloc for a terabyte, it's going to tell us we can't have it. That's too much. It knows it can't ever back that. It's not just a matter of sharing things or you know, promising multiple programs the same memory or anything like that. It just plain can't. It doesn't have enough memory in the system. So we'll get back a 0, I think is usually the return value for that. Anyway, get back an error code, whether it's 0 or like -10 or whatever it is, doesn't really matter that much. It's not a valid memory address. And so when we say R space at position 0, we're going to be taking that error code, assuming it's a memory address, and trying to change something at it, which should give us a segmentation fault or something similar.
Makes sense.
So that'd be another good question. Like, you know, what happens there? What else could be good? Oh, we can do a memory leak function. I should do a memory leak one after project 4. We got a function that does something and has a memory leak in it. I got to put enough code into the function so it looks kind of okay, but not so much that it makes it a lot to read.
Yeah. Not obvious, but not hard because you can't have something a page long and fully convoluted.
Yeah, it's got to have at least 2 exit points, I think.
Make it look like it's being free with one, and the other one's not.
It doesn't have to necessarily even disguise it, just at least 2 exit points, kind of. And maybe an exit point where you don't free it, like it hasn't been allocated yet or something. Because then if somebody hits free up there, say it's a 10-point question. If somebody hits free on the one that it shouldn't free on, that'd be like maybe worth 3 of the points to not do that. And each of the others could be worth like 3. And then the final one would come from having written free somewhere on the page. Something like that. Maybe 9 points would be better, because then it can drop into 3 for each exit point. I usually don't think about the point total and how it divvies up when writing the test, and I really should.
Let me guess, you think of some problems and then go back through and assign points.
The points are roughly proportional to how much work the project is, or the question is. So if it's really, if you can answer it in like a line, it should be maybe 3 to 5. If it takes you a page, that should be at least 10. And if it makes your hand sore, it should probably be more. But I know I can't have very many that make your hands sore.
Otherwise,
They
no one
take
will
too long.
finish the test.
Yeah, the networks test is always on the edge because it has significant coding parts.
Which is why Alex said they would be based on the final last time.
Yes, which was awesome, but I can't think of how you'd use it in this class. If anybody's taking networks next semester, he actually wrote common series bits of code that you have in network servers and brought scissors and a glue stick or something, I don't remember, and actually cut sections out and stuck them to his test. Right. Anything ever been from memory?
We have a zombie question.
Zombie question. Oh, yeah, we should have a zombie question. It's possibly covered up there. Yeah. Let's make them make zombies. We can make zombies with particular names. It takes a little bit of effort to make a program that makes zombies with particular names because the line that starts a program is remembered. So, okay. So if we wanted to have say a program that makes a bunch of zombies named particular names and then leaves them around for a while. Okay. It has to call fork. Zombie if you say fork, and then you might be the parent or you might not. So we say npid equals fork, and then if PID, then we're the parent. So that's the parent side of the world, and then else, and we're the child. Okay, but if we wanted to make a zombie, just kind of quick trick zombie making. All we have to say we're the parent. Let's go ahead and go to sleep for say 60 seconds. That's kind of a long time. And then we'll wait on the child. And weight needs a parameter there. So for the child, we'll just do nothing. Okay. Then we're done.
Don't blow your nose, James. Okay. Jeez.
So to build this, obviously there's a bunch of implicit declarations.
You probably have
It
to
recommends STD iota age. It recommends cis or types.h, weight.h, and stuff. Is that it? Almost. By the way, if you leave these things off on the midterm or the final, it'll be fine.
What the includes?
Yeah. That was the other major response to the networks test, is leave all the includes off, and that was fine too.
That's your first page, it's just all the includes.
Yeah, there we go. Okay, so the child's dying now. That happens. So it's called A.out, and you can see we've got a defunct one in the zombie state. So suppose you wanted to actually name it something in particular. Well, when you fork like that, it makes a new process, but the process has the same name as the old process. And this is determined by the name of the file that you run. So if we move A.out and give it an actual name, Fred, okay. And we go down here and look for process named Fred. You can see now we've got a zombie named Fred, which is the same name as the original process there. But fork is not necessarily the only way to do that. If you look for, not fork, it doesn't fork for you. Well, you can exec afterwards. You have to exec afterwards. Okay. Okay. So if we look for the exec family, you've got the ability to execute some completely different program. Now, we don't want to fork bomb this one. So we'll make a quick program call for the zombie. And this will be the actual program. So all it really has to do is just run. And that's it. Okay. So now we got A.out as a zombie program, but we could have named it something else like ZP. So there's ZP. Okay. Now in this other one, and I call this named zombies. In a child here, we said child is dying now, but we'll change names first. Okay. So then we can exec. Now we have to pick the right one in this family. So the exec ones, you have stuff like you can have a path, you can have an argument, and a variable list of more arguments with exec L. And all these have different ways of going about it. Exec P, you have a file instead of a path. So many of those things can work. But our file was at ZP.
Are you sure?
And then it needs an arg. And we don't really have to give it an arg, I guess. It doesn't need much of anything. Let's try that. Okay, we don't need that one. We need GCC, the main zombies. Okay. We didn't include the unit STD. No, we totally included it. Oh, it's exec L. Okay. Not enough variable arguments to fit a sentinel. Yeah, it needs to have a first argument, I guess, right here. That's the command line to run with. Then we can have a sentinel. Okay? We're going to do 0 for a sentinel. Missing sentinel. Is that the sentinel? No. Null. Is it got to be the null? Has this thing down here, this comment. Hey, there we go. Okay. We look for zombies. Now we got a zombie named ZP. Cool. but not quite changing the name ourselves. So then up here, before we do that, we could do this. We could say, we get the new name. Okay. Then we just have to exec something, basically copy ZP to the new name. Okay. That means we got to make a command line. Say, that's really long. Doesn't have to be that long. And then we can sprintf. Okay. ZP, ZP, 2%S. And so what we want to put into there is new name. Okay, new name. And so it can have a name. I don't know, that. Okay. So now we just have to run our command line. And then we have to run this with the new name. Okay. See what happens there. Finish the line. String literal and no format argument. Oh, yes, yes. It's kind of the place to go. Okay. There. Now we've got a zombie called Zach. Zach the zombie. So now we can make zombies with particular names if we want to. Anyway. So that's a brief review of zombies. So the next thing we just have to do is put them all and make like a list of zombie names.
Yeah, I was gonna
And then
suggest that.
just go through
Randomly grab from them.
Right. We can put them all in argv, so you have a program where you can specify them on the command line. Okay. So now this whole thing here, we need to be able to change our name there. Okay. There's our new name. So before and I equals 1, I is less than argc. The reason for 1 is the name of our program is actually the first thing in argc, so we want to skip that one. And so we will repeat this whole process here. And there's going to be an interesting issue right here. Well, no, there's not. Exec never returns. So we don't even need to write return right here. It won't happen because exec won't return. But if it did return, then we would start a fork bomb. So we'll leave return here just in case. Okay. So then we want to say new name equals argv at position I. And that should be type char star, and we should be fine. We can do that. Okay. See how that works. And so now we need some names. I have a cat named Kinky. Got a cat named Foxy. I've watched a cat named Sophie. So, well, I only see one of them. Oh, because the parent waits a long time. Right. The parent can't wait a long time there. The parent, if they wanted, could wait a long time here. But other than that, we've got to just keep going. There we go. There we go. 3 named zombies.
You got cat zombies now.
Yeah, zombie cats. Yeah. All right. Okay. Well, there we go. What else should I review? This is actually kind of fun. Maybe I'll do this more often. I don't know if it's any fun to watch, but it's kind of fun to do.
Come on, people. Now it's time to ask questions about things you want to know.
Oh, yeah. The different scheduling models. Oh, yeah, that comes from a day a while back. We didn't do code on it, so I probably can't have you write anything. Unless you write a scheduler on the, like in C or something. That could be pretty good. The block devices? Yeah. Okay. So in a class, we went through all of these things. I suppose if I were to have you write a scheduler, it would probably be best to just do that one. So It might be best asked as like a short answer or something. And so could ask, for example, what is the reason for prioritizing read requests over write requests in hard drive scheduling? I feel like that'd be an okay one. Because if you understood the whole talk about that, you can probably do it. It can be possibly created from scratch by a creative process if you didn't know. It's hard to make a short answer question where that's not possible. And you see the deadline IO schedule, for example, the read requests expire in a tenth the time it takes for the write requests, and so they've obviously been prioritized there. So the question is, why is that? Can you remember? Okay, this is sounding like a lousy question. Or, well, it could make it harder, though. Anyway, the reason here, if you have a read request, there's likely a process that's waiting for that to complete before it can move on. You have some program, and say it's supposed to open up some file, and it needs that file to actually work. The user has moved on to the next level, and for the next level, you got to load all the models for all the creatures in the next level, and so that has to come off the hard drive before anything more can happen. A write request, on the other hand, generally does not leave a process waiting. Typically, a write is like, okay, we saved the file and we're done now, something like that. Where if you don't get around to it for a while, there's nobody in particular waiting on that to happen. And so the system will tend to respond better and give better performance for a quick response to read, but much less so for write. The main motivation to eventually actually get around to the write is before the user accidentally turns off the power strip with their toe. It's nice if you've actually written the data. So that's why there's like a timeout here. But we'll actually put some stuff in. The other thing is, with a different program where to open up the file, it leaves a synchronization issue. You saw the struct file structures and how they have a dirty flag, which indicates that it's been changed in memory but not pushed to the hard drive yet. So if another program did open the file, it would be obvious that that file is modified and that the changes were currently in memory and not on the hard drive. So it doesn't, you're not likely to save something and open it up immediately with another program and get the wrong version of the file. If you're you save the file and you go do something else, then the operating system gets around it when it wants to. Yeah. So that's the reason for that. Maybe another one. What is the reason for merging together and sorting IO requests from different programs? That could be a good one from this stuff. Yeah. Yeah. So for programs make the IO requests, why do you bother merge and sort? Why don't I just take care of them in the order they come in?
Well, they have to merge because there's only one.
Longer than others to, like if you have a class that is going to take longer than another one that's going to take less time, then it will make more sense to do the one that takes less time to execute first and then get to the other one.
This is always funny when this happens. That's a good answer. I would probably give that answer full credit. But it's not the one I was thinking at all.
Oh, what I was thinking is the fact that, well, a hard drive only has like one communication channel. It's not like a hard drive has like 3 SATA cables connected in it. So it's got one channel it's communicating on, so all that data's got to merge, but then be sorted into its appropriate place.
Sorted in its appropriate place. Like, how are you sorting?
Well, you said, what's the purpose of it merging and sorting? Well, if it merged and didn't sort, well, then programs would be losing data into each other's file systems.
Oh, like off to the same stream there. Oh, the merging and sorting in this case is, you get a request from some program, and so you can leave it independent and pass them all, a stream of independent requests to the hard drive, or you can, reorder them on the way they go and ask the hard drive for something else first, like change the order to sort of, or you can take 2 requests and actually merge them together into the same request, which you do if they're requesting things that are really close to each other. If it's two things in the same track on a drive, you can just request that it reads the whole drive, and then it can be sorted out later. The reason for the sorting is if you have a, say, a sitting type drive, you got some kind of thing like that. It looks like a donut, and you got a head position. And so the head will tend to have a travel direction. So if it's traveling this direction, and you have requests, and say you have request, 1, 2, 3, 4, 5, you want to reorder these things. It's already going this direction. You want to answer 5, then 4, then 1, then 3. And then you switch direction, take care of any that have come in the interim, and eventually get to 2 last. So that's the reordering there. It has to happen. Now, when these things are put into a queue, you'll have some kind of queue. And so here's your queue, and it's being delivered to the hard drive. And so these things are put in here, 1, 2, 3, 4, 5. And so you got to swap these things. 5 actually gets to come first. 1 gets pushed back just after 4. 2 gets pushed back to the back. All these things get reordered on the way in. Let's see, I hadn't thought about Chelsea's answer, which is, wait a minute, but these things, when they come in here, I just wrote them as 1, 2, 3, 4, 5, but that's not necessarily how they are. Suppose actually 5 is huge and takes up most of this queue. And then you've got these other ones, and say the other ones are all little. Say, 1 is tiny, and 2 is tiny, and 3 is tiny. Well, you might want some of these serviced before it finishes 5. I mean, 5, these things go in a circle, but if 5 is reading a whole huge area out of this thing, you might actually want to put in some of these others, or, actually go take out the others and then come back and get 5, because it's going to take forever. And the queues actually do that. A number of these ones will have some kind of, each process has a queue, you merge across queues, intended for multimedia. But there's a number of deadline systems in here. This is probably the best example right up here. You got these timeouts on these, and so if you have a request that's expiring, it'll get bumped up. So if you got this situation right here, and then you got request 6 here, and say request 6 is, I don't know, there. It's an inconvenient spot. There's no reason to move it up, but if we're busy working on this giant request here, eventually we might need to say, okay, 6 goes to the front. We're going to take care of 6. Then we'll get back to this long one here. Yeah, that has to happen. I don't know if that's a super good question. I think it's a really bad question. Although sometimes with these, I've talked through this list of stuff several semesters, and so sometimes I look at this and I'm like, what would indicate a really thorough understanding? This is they didn't actually do a project where you wrote one of these things or something. Everybody actually forgot it within a week. What else did I talk about? There's a list of stuff again. We should do an interrupt question where I set a metronome, to click, 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 and every time it clicks, you got to go walk out of the room and come back in and get back to your test. And at the end, the question will be like, are interrupts annoying?
What's your
I
tricky
just ignore it because I don't operate on an interrupt.
Yeah, just disable interrupts. We got a little box at the top. Check this box if you want to disable interrupts for this test.
When you say tricky C question,
Yeah, something involving passing stuff around and something. I don't know if it'll take exactly this form, because I think I put one of these on the midterm already. And maybe we can make another puzzle. Different type of puzzle. Totally different type. I'm not very good at totally different type of puzzle. Okay, I think I got an idea for puzzle. Okay, so we've got a list here, and so we'll make this whole list global. We'll say int star numbers, and we'll say it's got 5 items. Okay. Stay away. Okay. So now I'll have some pointers into the list. So we'll have int stars. A equals numbers, B equals numbers plus 1, C equals numbers plus 2, D equals numbers plus 3, and E equals numbers plus 4. Okay, that took a little while. But now we've got pointers to each of these things that are A, B, C, and D. So now where am I going with this? Okay, they need to have values. All these things need to have values, equals. We go 10, 20, 30, 40, 50. Okay. So then we got to play a little shell game. At the end, we got to print out numbers. Okay. And so I'll slash n that. There's a lot of formats for printing these things. 0, I is less than 5, I plus x. Okay. There we go. Numbers at position, %sign D equals %sign D. Okay. I numbers at I. Okay. That should be pretty straightforward. Okay, so there's no trick in any of that stuff. But we have to have some kind of trick, or this wouldn't be any fun at all. Because that's, just wouldn't be too easy. Okay, so say, no, let's bring it. No, let's just bring it star. Okay, I'll call this one foo, and it takes in numbers. Okay, array called numbers. So then it's going to return numbers plus 1. Okay. But it's also going to take numbers at position 0 and set that to, say, 67. Okay. So then we can say something like B equals foo of C. Star B equals 42. Okay, good enough. Okay, so then the question is, what's the print?
These are the hardest questions for me. I always get lost track of the last thing.
All right. So the first thing to look at is like which 2 did we actually change? You can see we only changed. Well, okay, we made 2 assignments. They could assign to the same thing, but they don't. They're different things. I just got an idea to make it better, but I won't go change it. Just won't change anything. Sorry. Oh, yeah. I'm just correcting it to mean what it looks like it means. Okay.
Okay.
I kind of assumed that anyway, even though it's technically.
Yeah, I figured everything did. I did.
So the first entry will be 67. And then
I get it.
the second should be 42. 67, 42.
Or you got a guess? Oh, you got your hand up.
Never mind.
67.
Yeah, let's see.
Okay.
67, 42. Oh, wow.
Yeah, you figured it out. That's pretty far off.
Me too. Okay, moving on.
So the key on here is we've got a local variable, a parameter called numbers, and we passed it C. So C up here is numbers plus 2. So this numbers here is advanced a couple over the other one. So when we say numbers at position 0 equals 67, it's much different than, suppose we sit over here, numbers 0 equals, say, oh, I don't know, 32. So if we say that, okay, puzzle, run it. It doesn't have any effect at all, apparently.
That's okay. Well, yeah. Because at 0, that's 32, and then, yeah, the first time you invoke foo, you're passing it C, which is numbers plus 2, so it's going to be the third position. So 0, 1, 2, yeah.
That one over I hate them.
That's
Yeah.
what I thought. How come
Yeah,
number
should've.
0 doesn't
Did I first say it?
start with A? Because you should start with
I was gonna say,
zero.
There we go.
It's like, I'm like,
Yeah, like, oh, logic doesn't work today. Okay, so anyway, so number 0 up here refers to that, and the fact is it also does down here. So let's change number 1. Show you that this is all normal. Number 1 equals 456. So if I actually save it up there and run it, you can see numbers at position 1 is now 456. So numbers is perfectly normal everywhere in here except right in here in foo, because we passed it C, which is numbers plus 2.
Okay.
So
But then
C,
you modify number 0.
Because numbers is an array.
yeah. So with C, yeah, suppose down here, we'll go down here again, and we'll say C. The thing C points to. Excuse me. Oh no, let's say C at position
Because the number
2 equals 1,000.
Because we control numbers to the 0 position, because we add 2, it's also 2.
So you see C at position 2 is numbers at position 4. Because C is numbers plus 2, so they're all advanced a couple down it. So when we're up there in that function, we say numbers 0, we're actually saying the same thing as C. And so since C is numbers at position 2, that numbers at position 0, that's 67, refers to the same thing as C, which is numbers at position 2. Then we say we go ahead and return numbers plus 1.
Which returns D.
Which returns D, yes. So
And
now
then
B
you
is D, and we just changed what that points to right there. Yeah, so D is 42, since B has now been changed to be the same as D. So if we were to say something down here, we say,
Which
yes,
means, based on the way it is, if we
You have me confused. So foo is going to return,
foo returns a pointer to D.
yeah,
The pointer D.
yes, and B becomes.
B
yeah,
becomes a pointer to D instead
yeah,
of
so
being
they
a
both
pointer to
point
B.
the same way.
Instead
Right.
of being a pointer to numbers plus 1, it becomes a pointer to numbers plus 3.
Yeah.
So you actually have 2 pointers to numbers
The
plus
same
3.
thing,
Yeah. So then when I put this in here, if they're the same, turn out they're the same. It says they're the same.
I will still probably get it
Same here.
wrong. No, I will try. I promise I will
Yeah, the
try.
part that was tripping me up too is the return.
Well, you
return
know, if
numbers
you
plus
It's like I knew that return numbers plus 1 did something, but until he ran it and I stared at it for a few seconds more, I wasn't sure what it was doing.
One very good way to help us would be to not call the numbers thing in
Well, that's
full numbers.
actually the whole point. That's the whole
I
point of
know,
it. That's
I
the whole
know.
point of it being a puzzle.
I know, I'm trying to get.
Because
3
there's,
points
well,
here.
the thing is, the reason why they're written in such a way is to be confusing, is because that's how you make a puzzle.
Isn't the numbers at the top though
I'm
like
still
a
trying to
global
get 50
variable?
points for writing our names on there.
But you
That
can
was
still
nice.
create a, I guess you can still create a.
You can still
Oh, yeah,
create
yeah,
a local
sure.
Yeah,
variable.
no, see, Seth, that's something, now your return on your foo function saying numbers +1, that would initially make me think, well, are we be increasing the array size by 1?
No.
Yeah, that's the memory address.
It's because numbers is a pointer, not an integer.
Right, but then, okay, numbers +1 refers to
The
what
next thing,
exactly?
the next thing in the array. It's a pointer to the next item in the array.
Yeah.
The next memory address. Because when you +1 a memory address, it doesn't add 1 to the memory address. It adds 1 of whatever the array type is to the memory address.
Yeah.
Okay, and so since you referred to numbers of position 0 first before the return, then it's going to be the second one.
So here would be a great multiple choice question. It's something like this, where you have some int star and you add to it, and you ask how many bytes does this, well, maybe that would not be good. Try to make this really, really super clear. So I want to say, like, how many does this actually add to numbers?
It adds
One position.
32 bits.
Yeah, so numbers, since it's in bytes, like the memory addresses are all in bytes. That's
Which would be 44.
4, yeah. So it's maybe a good multiple choice question. 1, 2, 4, 8, I don't know, 365. Sometimes I'm running out of steam by the last answer of multiple choice.
Yeah, that has been noted a couple of times. Where it's like there's like 3 or 4 answers that are like, these are in the realm of possibility. Then there's one that's just out of left field somewhere. It's like, well, do you know that one's the wrong one?
Right. Occasionally I try to make all of the answers kind of similar except for the one that's right.
Okay, now it makes a little more sense on how that was lining up, because when you're saying B equals foo and you're handing it C, and then it's also returning +1, that's why it's D.
Right. You can also just say B equals foo. And then maybe a good question would be, why does this cause a problem?
Because you're making a pointer equal to
A function that's not getting a
function.
parameter.
Oh, interesting. It didn't crash.
It still runs.
Yeah, how the hell did it not bark at you because you're calling a function?
It just made B.
And the function requires a parameter.
Oh wait, no, yeah, it didn't actually. It just changed the things. It just never ran foo.
Well,
because you don't ever call
run foo. Yeah. Oh, we didn't try to call, but I would have thought that would make a problem. So you're changing the spot
It made a
where
warning.
foo is stored. But apparently that didn't cause an actual seg call.
It just
so
makes a
we could,
warning.
like print out since line D.
No, it did change B.
This will be int star foo.
It didn't change numbers in
Right,
position
right.
1. It definitely changed what B is.
That's the thing at my suit. And yeah, we did actually do that. It was type of what I needed to. Okay.
42.
Yeah. So now foo is actually 42.
You changed wait. You changed the entire function into a number.
So now if we say that, we're gonna we gotta have a problem at that point.
Because foo is no longer a function. No, it still works.
It still runs.
I think it probably just optimized it out because it doesn't do anything.
Kind of.
Makes you wonder exactly what's going on under the hood.
In some cases.
Didn't break.
I mean, it broke, but it didn't break in the expected way.
Well, yeah, I mean, they can't run foo anymore because foo is now 42. I wonder if we're hitting a machine code thing and this happens to return or something.
Maybe. Just had to, double compile it just to make sure.
Yeah, apparently. Well, yeah. This is getting out of the realm of a very good test question now.
For lunch today, it's spaghetti.
Extra credit? Oh, like, sure, like extra
Why
credit
is
right
this not
here.
breaking the way we think it should?
Oh, here would be good extra credit. Char star foo equals, okay, fill this in with a string that is valid x86 code for foo.
Oh no. Oh, good lord, no.
Let me get CS250 question.
Yes.
Or maybe security. For security, we actually make a program response shells that can be put into a string.
Sounds
Yeah.
slightly nightmarish.
So anyway, I keep thinking of better and better ideas for how to make a really tricky C puzzle. So we should probably stop reviewing that one for the moment.
I would say so because it's getting to the point of terrifying.
But I think the first one is probably kind of reasonable. I just kept being tempted to enhance it, but then left it as it was, and I guess it was a good enough C puzzle anyway. I'm not sure anybody was sure they got it. Maybe somebody did, and doesn't want to say, which is perfectly fair. What else should we review? Everybody's feeling more comfortable about the test, right? Like this is going to go really well.
No.
That's what review sessions are for.
Yeah, but the thing is the more you start tinkering with stuff, the more amused you're getting, and the more afraid we are.
Yeah, we write a fork bomb.
You had a fork bomb on it, Tim.
So interrupts.
Yeah.
Should I just bring an entire page of all the interrupts I could possibly be in it, so I got that all locked down?
Well, I've run against about numbers, like, what interrupt number is used for such and such a thing. Interrupt 80 is probably the only one that anybody might remember, because that's the one used for system calls. But I wasn't planning on asking about interrupt 80 specifically. That said, a good question might be, describe the role of interrupts in a system call and explain how this affects performance.
Okay.
Because system call requires the interrupt, and then you can talk about that. Or might be trying to think of a good timer question one. See, if you have something you want to have happen in the kernel doesn't really invoke itself per se once the system's up and running. It needs some event that will take place in order to make it do something. So for example, with CPU scheduling and process scheduling, the process continues running until it gets stopped. And the kernel can't just step in and stop it. So what the kernel does is set a timer to give a series of regular interrupts. And in each interrupt, it can reevaluate what's currently running and decide to schedule it again or do something else. So the interrupts are actually critical to process scheduling, but if they happen to frequently, you keep interrupting the process again and again and again, and it can't make any progress. On the other hand, if you interrupt it too infrequently, then if you have some background process, it can get itself going on the CPU and run for a long time. So then if the user is trying to do something, then they can't necessarily do it right away. So it sort of depends on what the computer is supposed to be doing, interactive performance versus it's kind of sitting in the background and running Towers of Hanoi for a month or whatever. And so real-time operating systems, which Linux is not. We didn't talk about real-time operating systems all that much. We also never talked about Android. Usually I try to get Android in this class at some point. Anyway, real-time operating systems guarantee a response within a certain amount of time. And so that requires interrupting the current processes and taking in your request for CPU time and guaranteeing that they're fulfilled at some point. Obviously, if you give it too much stuff, there's no way it can be guaranteed. But in general, if you have, say, really important events and not so important events, and you flag the really important ones, they have to happen within a certain deadline. This has to be done within 100 milliseconds. The real-time operating system might make sure it happens. That's why they use them on fighter planes and things like that. If you've got a missile coming in, and it's got to deploy countermeasures, it's best if there's a guaranteed time within which that happens. So I don't remember if we did this exercise or not in this class, but sometimes I like to look up and see what operating system do fighter planes run, because they run operating systems. And it'll be a proprietary real-time operating system of one sort or another. Anyway. Oh yeah, so that's kind of things to ask about interrupts. A kernel interrupt handler, I never had a kernel interrupt handler question on the test before, but, what's that?
It's not, maybe not the time to start. It's okay.
Well, it doesn't necessarily have to be a hard question. I mean, it could be just, write an interrupt handler so that whenever an interrupt is received from the network card, and I'll disclose an interrupt, like interrupt 42 or something, the mouse cursor moves up and down.
That's lab 3, isn't it? With the, like when you receive a signal and then it changes the function of the system.
Was that lab 3? I think it might have been. I think you might be right there.
If it's there, you can put that.
Catching 6. Oh no, that was 6 SIG-B. That was different. That wasn't interrupt. That was signals. See, like, yeah. Yeah. So this is signals, not interrupts. The signals are a higher level Unix mechanism, and we looked through how those work. But like if you control C something, it gets sent a sig int, and so that signals the process. And if the process is a handler for that signal, then it runs the handler. If the process does not have a handler, for sig int, it terminates it. For some of the signals, they're simply ignored. They have different effects depending. Yeah, and that was a good one to ask, because if you mix up signals and interrupts, that'll make it hard to get these right. Where are signals in here?
That was September 6th.
I know there was a question about it on the midterm.
Yeah.
I suppose we already asked about that then.
Yeah, there was a whole thing about signals on the midterm.
Yeah. I thought it was a good one. I haven't decided what kernel module should be written on the test.
What kind of question do we have about bootloaders?
Bootloaders have to be really simple, since we didn't go talk a lot about these. Like maybe, yeah, so I said maybe multiple choice. Maybe something like, say, what is a common role for bootloaders as a multiple choice? Loading the operating system kernel into memory has to be in there because that's something it does. There's a few other ways you can describe what bootloaders do. For example, most of the bootloaders will let you choose between operating systems. So they give user interaction and allow the user to decide how to boot things. They got to be able to look into hard drive file systems incidentally. So one thing they have to be able to do is include file system handlers. Typically they're kind of more primitive. Like Grub, for example, you can't use a riser fs partition to, well, maybe you can riser fs. You can't use a B-tree fs file system partition. I know that's true. To store your kernel with Grub, because the Grub bootloader can't read the B-tree fs partition. So that could be good. It has something they don't do. They're pretty sophisticated, so I have to think a minute. They don't do 3D graphics. It's one of those things where you're like, oh yeah, what do animals not do? Animals don't use tools. You find an animal that doesn't use a tool. Animals don't bury their dead. You're like, oh yeah, there's a cat and it's burying a rabbit. Well, it's not the same species, and it just eat it later, but you know. But there's all these funny pathological little cases. And so I'm trying to think of a clean thing that bootloaders don't do. They don't format hard drives. Is that true?
It's really bad when you have to question yourself about the declarations you're making.
I have to think about that one a little bit, trying to come up with a thing that they really definitely don't do. I've got a problem with these. So I didn't say anywhere in the class, for example, that bootloaders contain a graphical user interface. Typically they have like a text-based interface, but it supports arrow keys and things, and sometimes a mouse. You can put that there. Or bootloaders don't support 3D graphics or something like that. But then somebody in the class is bound to find some counterexample somewhere and be like, oh, this question is totally invalid. I know a bootloader where you can play Quake inside it. Look, here's a tutorial for Grub. Here's a YouTube video of somebody doing it.
I was to say, so a bootloader you can play Quake inside of, that'd be the perfect one for you, wouldn't it, Seth? Just play quick while your operating system's loading.
Right.
Pretty sure.
I have to think a little bit about it if I want some definitive
Instead of
declaration.
typing in a password to log in, you gotta complete the level or something.
That's Namco copyrighted where you play like a little arcade game while
Loading screen games.
Yeah. You can have something like this.
It's so much
The kernel is loaded into memory by, multiple choice. The GUI, the bootloader, BIOS, itself, bash. That could be.
I mean, that's not a bad question, actually.
And some of the answers are a little ridiculous. I didn't think about it for all that long, but I think it's worth. Very decent one. Anyway, that's the kind of thing I intended to ask, not to write one. We did have one semester this class. It was not the last iteration, but the one before it, where we actually looked through the Linux boot process in some detail and asked a more detailed question about it. But we didn't do that this semester. The thing is, this class could easily turn into multiple semesters, and the same is true of pretty much all the upper division classes. And so it varies a little bit what exactly it covers, and partly it varies based on the textbook. It's nice if the textbook backs up whatever we're talking about up here. And so that particular semester, I picked this textbook on the Linux 0.11 kernel, and it went over the kernel basically line by line. It was a pretty good explanation of, in detail, what an operating system does. But everybody hated the book.
That sounds like it would be extremely dry.
I actually thought it was pretty interesting. The book was structured funny, though. It didn't really have an introduction, like an introductory chapter. It just sort of launched right into it, which made it a little hard to be oriented unless you already knew what it was talking about.
That's probably why we didn't know.
Yeah. Yeah, English was also not the original language it's written in. It had been translated, but sometimes the translation wasn't absolutely accurate,
Oh.
or just, it was accurate, but it didn't use the expected words.
So I had a little bit of English problem.
It is a little troublesome in some ways.
What?
No, that's fine.
So yeah, we talked about most of this stuff now. Oh, we didn't even talk about read and write functions. We've been doing read and write functions on Frog forever. So they should be really easy if I ask a question on those. Write a kernel module that reads in names and what's it do? Crash your computer if they're too long.
Isn't that every kernel module? I mean, when I didn't have the buffer set right on one of them, it crashed the computer as soon as the module was inserted.
Right. Right. All right. I can give you that. Remember that demo we did with the solitaire stopper thing? Modify the sol stop demo by adding a read function that allows you to read in from a proc file the name of the program you want to block, so that it's changeable.
Oh, jeez. Yeah, but then people find out how it works and they just put in something like explorer.exe and just make the whole operating system fail.
Yes. Yeah, that would only take about maybe 3 lines of code to do. So it wouldn't give you a sore hand unless you're doing it seriously wrong. Although sometimes when I come up with these questions, I'm like, oh, that sounds complicated. Nah, that's fine. You can answer it in 3 lines. And a lot of people see it and they see a solution, and it's a great solution. It works good, but it's like 100 lines. Well, everybody sees a different solution, you know, when you look at it.
Yeah, I think that's one of the problems a few of us have ran into with some of the coding questions.
Right. I had a solution in mind that was simple and easy, but sometimes people see something more complicated first and go for it.
I know there's been at least one question I've answered in one of your classes where it's like, I find out later on after the on the midterm or something that, oh yeah, the solution for this took these 3 lines of code. And it's like I look at my solution that's like half a page of code, and it's like.
That's usually why I bring extra paper. Most of the time on a test, I've had the occasional counter time when this wasn't true, but most of the time, there's enough paper on the test to answer it, even in a fairly large font size, if you think of the answers I thought of. So you find yourself being like he included an inch, and I need like 3 pages. It might save you time to think about it for another minute before you get started. Yeah. That was one where I was pretty sure that most people would end up needing extra pages. That I kind of wished I had like legal paper or something for that exam. I don't think we even have legal paper here. I'm not sure our copier supports it.
It should.
It should.
Just means may not have it loaded and it may not have the settings set because it's for an enterprise level copier of any sort.
Okay.
It supports it.
Even for ones that run the papers sideways?
Should.
Okay, so you'd have to make the whole mechanism wider for it, not just support greater length.
Depends on your pull mechanism.
Okay.
It really depends on the feed mechanism in the thing.
I should go get like a ream of it just to make something on legal paper. Because my son's initials are LGL. He's practically named after a paper size. Okay, anything else anybody wants to cover? We got 5 minutes.
I have no idea.
Okay.
It's like I'm never sure
Thank
what
you.
questions to ask, and that's
Okay.
probably the worst problem about it. So I'm glad people had some decent questions.
Yeah, actually there were a lot of questions that were pretty fun.
Can we get an example of like maybe the arithmetic, the binary arithmetic?
Oh, yeah. Yeah, I actually spent like half an hour thinking about binary arithmetic yesterday. Okay, so suppose you have a couple of numbers. It's easier if you start out of hex on this stuff. You can use non-hex. I mean, I could say something like, you start with, say, 65, and you're going to OR it with 42. But it's, if they're a decimal, it's just extra thinking that you don't have to do. We'll pick a couple of numbers in hex. 0x, say 103, bind bitwise OR with 0x, say 2e. Okay, so what's the answer there? What's that equal? I was tempted to put them vertical, like with the OR over here, but I've never seen anybody draw it that way. And so that seemed a little odd. But regardless, we'll go ahead and draw them out. So the 103 here, I want 103. Let's not do 103. That's 3 characters. Let's just do 2 characters. We don't need to make it too hard today. 55. Okay, so 55.
So the highest numbers are 2.
So 0, 1, 1, 0, and for 5, then 0, 1, 1, 0. So that's 55.
Oh, that's right. That's how it's 5 and 5.
So that's that one. Then the other one,
I forgot.
2e, is, so the 2 there, 0, 0, 1, 0. That's the 2s, 1s, 2s, 4s, 8s. Then the e. So the e is the second highest one. If you remember it's the second highest one, then it's easier. Because the only way to get higher would be to make this one a 1, and then you'd be a f. Okay, so we ORed them together. OR. Okay, so 0, 1, 1, 1, 0, 1, 1, 0. So that's it. And so let's just come out 2. So this is a 4 and a 6. If you see it, not 6. A 4 and a 2, which is 6. And that's actually E still. There you go. So maybe something like that. That's kind of a review of 250 kind of thing. It'd be better to turn it into a story kind of problem. Say you have a device that you've recently attached to your computer, and you're not actually sure what the device is. You were in an airport, and you're past the security point. So you're bored because you had to leave all of your knives and explosives and things behind. And so behind this plant, you find a device. And you can see at the bottom of it, it's actually got a PCI Express interface. And luckily, you've got your desktop computer with you, so you plug in a device. Now, the device had written on it that you ought to set the control register's third bit to 1 if you want to see something amazing. But you shouldn't change any of the other bits. It's got a warning about this written on it. So you want to use in order to set that one to 1, you want to use a bitwise OR. And you want to set the third bit over, third bit. So what do you OR it with in order to make that happen?
So how come there's 0, 1, 1, 0 for 5, and then it's 6?
Yeah, I was just looking at that too.
Oh, good point, because I made a
0, 1,
mistake.
0, 1.
Yeah, that's why.
And the other part of
Okay,
55
so the
also?
second one is, it's 55, so it's 2.
Yeah, I was just Googling that. Like, that doesn't look very much.
There you go. Good observation. I think I only get like 5 out of 7. That could be worth more than 5 out of 7. A lot of times there's a thing in these questions that's recognizable as a arithmetic error, not a process misunderstanding. And if I can conclusively determine for sure that it's that, then your answer is worth more than if it has a mistake in it and it's not clear whether you understood or not. And I realize this is like super fuzzy, but that's how partial credit is. Sometimes. Oh, sometimes it can fall into a similar range by some kind of strange process. So if it's asking this whole thing here, and then instead of this one, you answer like 0xf7. It's like, that could have been a mistake right here, but if I can't see any of this part, you know, like, why? So that's why you show your work on these things, just like math.
After 6 times 6, I don't know the rest. Because when I was in elementary school, I knew how to count. So I don't know. After 7 times 8, I don't know.
Oh, really?
Yeah, and I'm about to.
Oh, so what's 7 times 8? Like,
I don't know.
Uh,
864? I think so. So you see, I told you. I don't
oh,
know.
yeah. See, I don't have it memorized either. So, but I usually have to figure out by counting from the closest one I do know.
7 times 7 is 49, so you add 7 to that. And yeah, I guess that's good. You see, that's
54?
why I don't want to
No.
I don't want to look at it.
56.
But when you look at it, I don't know.
Okay. Yeah, I am actually done. It's like the time.